Hello, everyone. Thank you for coming to my talk. I'm going to talk to you today about legacy phosphorus in Lake Okeechobee. I want to thank my co-authors for helping collect the data analysis, and overall discussion. I also want to thank South Florida Water Management District for funding for the data collection. So before we really jump into this, I want to acknowledge the lands in which we conducted this study as well as live on. I'm presenting from the historic lands of the Calusa, Fort Myers area. And, the Everglades, as we know it today, is rich in the history and modern traditions of our First Nations. From the Calusa, the Tinau, the Tequesta, the Miami, the Cocada, the Jaga, the Miccosukee, and Seminole, these lands are the Everglades and are steeped in indigenous history. We pay respect to their elders, past and present, and extend that respect to their descendants, to the generations yet unborn, and to all indigenous people. We recognize the ongoing relationship of care that these indigenous nations maintain with this land and extend our gratitude as we live and work as humble and respectful guests upon their territory. We acknowledge and thank the Miccosukee tribe of Indians of Florida and the Seminole tribe of Florida for being stewards of this traditional history and territory. So now let's get into the science. So historically, the Everglades, as we've probably heard enough today in this conference, is that in historic times, in the wet season, water would overfill the lakes in the Kissimmee chain of lakes, flow into Lake Okeechobee. Lake Okeechobee would overflow its banks and flow south along the peninsula. And doing so, these vegetative communities have established. Swamp forests, sawgrass plains, and southern marl-forming marshes. However, since flood protection, drainage, damming, diking, and draining, this system is vastly altered, changing the flow regime of the lake, well, the physical structure of the lake with canals and dam and dikes and water control structures, but also the hydrodynamics of the system. Some of those historic vegetative communities still remain, but it's vastly minimized. Throughout the past 40 some odd years of history, Lake Okeechobee has undergone some changes in operations. Here are just some general acronyms associated with that. Each operations plan had its own special unique way of moving water or storing water within the lake, and we're currently working on a new iteration of that. Along those 40 years, we've also had changes in regulatory programs for Everglades restoration and water quality improvements. And we've also seen extreme climatic variability during this period with El Nino and La Nina periods of intense tropical activity, as well as droughts. So the system, here's a couple plots of inflow and outflow loads and concentrations over the past 40 some odd years. Since water year 1979 to 2020 is when I updated this. And so we see this top panel here is discharges. The red is inflow, the blue is outflow. And you can see generally, kind of, if you squint, some years, what's going in is what's coming out, generally, respect to water. These middle panels are load. So this is on the left is total phosphorus load, same color scheme as discharge. And on the right is total nitrogen. And on the bottom is TP flow weighted mean on the left and TN flow weighted mean on the right. And you can see the extreme variability, and that's going to be the buzzword of this talk, that we've seen over the period of record between inflow and outflow. And at that from a trends perspective, not much from a trend perspective for inflows. So those red dots, if you try to draw a line through them, you're not going to see a significant monotonic increase or decrease. They're because of that extreme variability. So that's why we have the Kendall tau and the p-value here. Only p-value that's less than 0.05 is the TM flow weighted mean. And then on the far right is the rate of change, so the Thiel-Shen slope. And so you can kind of use these as a gauge of if you're not comfortable with looking at significance per se, you can see the rate of change in the system in that time series. Now, if we look at outflow, so those blue dots, we can see that we actually have a significant increasing trend in phosphorus load over this period of record. The outflow phosphorus, so those blue dots are significantly increasing. And the TN flow weighted mean concentrations, both inflow and outflow, are decreasing. Now, if we look spatially across the lake, so taking that same type of analysis of Kendall trend and Thiel-Shen slope, we can look across the lake and make some pretty graphics. So to orient you guys, here on the left is just general trend, the trend analysis over the 1997 to 2020 period. On the right is that average geometric mean concentration across the lake. And so the colors here, the shade shows us the Thiel-Shen slope for TN here on the top, in the middle, total phosphorus, and on the bottom, chlorophyll. And those dots here on, at least for the trend, if they're different colors, and I apologize if you're colorblind, because the green dots are p-values greater than 0.05, and the red dots are p-values less than 0.05. And you can see, at least for nitrogen, we have this trend, significant trends across the center of the lake, ranging from, well, they're all significantly decreasing. If you look at this scale on the Thiel-Shen slope, we actually have decreasing trends in nitrogen across the lake, which correspond to decreasing flow weighted mean concentrations coming in and out. For phosphorus here, that's a little bit of a different story. We actually, most of the sites, we don't see a significant monotonic increase or decrease, but we do have 3 sites here in the southern part of the lake that we do have significantly increasing trends, especially in this southeast corner of the lake. And you can see here the phosphorus concentrations within the lake spatially in the water column have are different, I guess you can call it, for lack of a better word. You can kind of see where the pelagic zone, so the center part of the lake, is the highest part, and then the littoral zone, or the area around the lake where we have wetland littoral vegetation, is actually a lot lower. And then the chlorophyll trends here on the bottom, we have a smattering of trends that are significant, as well as the directions of them. Now, if we look at the sediments, so here's just a general spatial interpolation of the sediment data from 1988, 98, and 2006. And as you would know it, during 2020, we were in the middle of collecting the data, and then coronavirus hit and kind of put a wrinkle in our plans a little bit. We have some of the data collected, I think most of the data. It's just a matter of getting those laboratory analyses taken care of. But you can see here on these plots are all oriented the same. This is Lake Okeechobee. This area that's outlined is a littoral zone. And then in the middle here is a pelagic zone. And if you look across, you can see with blue being the highest, as in 1,300 milligrams per kilogram of phosphorus, and the yellow and light green being low, less than 200, you can see that the low area is generally within that littoral zone. And then in the middle is higher. And that's driven mostly because it's the pelagic zone, but also because of characteristics of that sediment. So this sediment here is more muddy, and then the liquefied mud, I guess you can call it, than the littoral areas, and is more susceptible to resuspension. Now, another way to look at that is looking at it through a general additive model, and this is work in progress. And so with general additive models, you can actually really tweeze out these effects. And so granted, we only have 3 years in this model, and a 4th year would make it a lot better, make us feel a little bit more comfortable with kind of this trend. But generally, you can see the effect of year only is decreasing, which is good overall. But and then you can look at it spatially, and you can kind of take a guess at where the high effect area is, because we have this pelagic zone here, and I apologize for the quality of this graphic, but the yellow and light green is high effect. The blue, purple is low effect. And you can see that for the spatial structure of the data, the pelagic zone has a greater effect, positive effect, and that littoral area has a lower effect on the structure. So taking a look at kind of how we have the water column, we have the sediment kind of characterized, and we have that interplay between the two. So the internal loading, you can look at the net P sedimentation coefficients through the period of record, and this takes into effect or account load, basically the in load, the outload, and what's currently in the lake in the water column. This is water column only. And you can see that when sedimentation rates are less than 0, we're in the sediment is kind of a source. If it's greater than 0, then the sediment's considered a sink. And more often than not, we are at that period where the sediment is as a source. We can look at it another way. To have this spatially averaged concentrations of total phosphorus across the lake, this red dot and line combination. And then we can take a look at a simple model that only takes into account internal inflows, essentially, which is this Volden-Weider model here. And so that model really doesn't take into account biological processes or cycling or anything like that. It just kind of says what's coming in and how does it settle out. You can see that the lines here are, number one, they're very far apart, but number two, they're diverging. So saying that essentially what's kind of telling me, and maybe you too, is that the sediment is a pretty good source, and it's fluxing out into the water column at greater rates. So a lot of current ongoing restoration efforts have taken place over the years. We have the total maximum daily load. We have the watershed construction plan, which identified ways to reduce phosphorus loads into the lake. We have the basin action management plan that takes that another step further. And then we have the new Lake Okeechobee watershed restoration project, which identifies, it's not necessarily a water quality driven project, but identifies storage as well as restoration of wetlands and reduces that freshwater release. So a lot of restoration, a lot of focus has been on nutrient reduction into the lake. That being said, Lake Okeechobee is a highly dynamic system affected by pretty much the legacy effects, inputs, what's been put in before, as well as management. Phosphorus as well as nitrogen inputs are highly variable. Like I said, that's the buzzword, driven by upstream inputs as well, and kind of really has a potential to impact downstream systems. Within the lake, TP and other parameters are, again, variable, but driven by ecosystem factors, structural factors. So we see within the middle of the lake, and this GIF here on the right goes through the water column. Phosphorus shows that the pelagic areas, the center part of the lake, has higher concentrations in general than the littoral zones. And added on top of that, you have impacts based on inputs. And then for the sediment, again, we have both spatially variable, but also temporally variable conditions within the lake. And this spatial trend kind of really mirrors that water column trend that we see in the above GIF. And so the difference from inputs to outputs and the water column to sediment interplay is really driving the phosphorus in the system. And so the internal loading especially is really affecting the water. The internal loading is in phosphorus fluxing from the sediment to the water column is really driving what we see in the lake today. Thank you for attending my talk. I know that was kind of a whirlwind blow through of data, but if you have any questions, feel free to answer them. You can either reach me at my email or feel free to hit me up on Twitter. Thank you very much, everyone.